So good afternoon everyone. I am solving the card poll problem of reinforcement learning today. So basically, this is my script and this is my Jupyter notebook, and I just have solved some concept over here. So actually, the Q learning implementation is. Or let's say the Q learning approach for the classic card problem is uh, best understand by the example itself. So basically, if I run, so this over here is cart and this standing one is pole. So the cart moves and it is attached with a stick. The goal is to adjust the stick by taking the action left right by applying the force, and then adjust it as long as we can. And this is a kind of solved by the Q learning method. Q learning is iterative algorithm that is solved iteratively by storing its value in a table. And let's see the how it can implement it. So basically, first of all, we need to understand how to work with the Q learning. And the Q learning is very simple. For any state, and we take action. If we are in any state and we need to take the actions, we just take the actions randomly by going to the new state, and the new state has the best value for the new state is computed by the max of a q of st plus 1a, and we discounted that over with time. So the latest will get much more value than the farthest, because the lambda will be multiplied. The lambda power some step will be incremented, so the next future will be much more given priority, and the farthest will be discounted much more. So and the reward that it obtain after we get weighted by the learning rates. Basically, if the learning rate is high, reward is not much more like weighted less. If it is very less, then we just make it much more small, like we weighted a small value, and then negative of that will be if we get the 1 value over here, and then it will be 1 minus 1 0, the coordinate will be 0, which means that if the value is very high, if the value is very high, it tries to exploit more. Exploit none means it won't use this previous value. It just forgets everything, nothing from the past. So basically, alpha is very dangerous over here. And then okay, let's see the coding part. So we import the gymnasium as a gym from the OpenAI. We make the environment render mode is human, or it can be RGB. Human means the actual port and cart and the pole are seen after rendering by using the Pygame library. And the number of buckets is kind of, we need to bucketize the environment or discretize it. For the discretization part, we are discretizing 10 40 means for the card positions we are taking the 10, which means that our 1 second is 1 second, and their 1 second is 0.2 times 0.2 value. Actually, which means that within 1 second there will be 0.2 of 0.2, so 5 steps will be encountered, which means that we need to switch. And then the card position as 10 value means within a continuous space, within a continuous range of value, we take the 10 samples within that time period, within that tau value, within that small amount of time we sample 10 such values. So basically, if there are infinite number of values and we need to sample only 10 values within that second, so basically in a second there are this much of value, but we cannot handle all of them. We just sample that. That's kind of bucket. For each parameter, card position, card velocity, port angle and port velocity, we have 4 kind of variable to work with. And then our actions has two there are 2 number of actions, either apply the force left or apply the force right. And then these are my computations. And then state bounds is kind of bound. So basically, card position bound means the card cannot go beyond the minus 4.8 or 4.8 the right of the screen. Similarly, velocity and put. So basically, This value is around I guess 22 degrees. So pole cannot go beyond the 22 degrees left or right in angular manner. And then Q value table is initialized with the number of buckets plus number of actions. So we have Q values kind of stores every computation. Initially all the values will be zeros, and then that value will have a size. For our case, let's just compute some. Let's just to compute the how many number of entries will be there. There will be 160,000 number of instances, and in each of the state we can take either left or right action, and then that's a kind of 1, 2, 3, 4, 5 dimension table, and then we computed this size within some radius function. So basically there will be a 5 dimension table, and the total entries will be 160,000. So as you can see from this example, if the bucket size increases too much, or the state or actions or the actions increases too much, the true value increases. If there were like 100 different kind of actions, then it will be 16 million. So that will be too much big array, and to hold that in memory will computationally expensive. So the Q-learning method is not suitable for a very complex environment having high number of states and actions. And as you can see, now let's define the hyperparameters. The minimum acceleration rate, minimum learning rate. This acceleration rate is to take the actions. What actions to take? So actually we are using the epsilon greedy policy. So basically we are I will just explain that in detail over there. But let's say that this value is used to take the what actions to take in a particular state. This is actually randomly, like there are two paths to move, left or right. So which path to move, we can take it randomly or some kind of deterministic manner, right? It's very simple. And learning rate is how do we give the exploitation of the previous resources. If the value is very high, we exploit all the knowledge. If it is we exploit very less. If the learning rate is 1, then the learning rate is 1, then our previous past states will be forget immediately. If it is very low, then our previous past states will be used for the exploitation part, because we give much more priority to past states than learning new things. So basically, if the learning rate is low, we learn less, we exploit more, we explore less, exploit more. And then episodes is kind of how many times we reset the environment, and then try to balance the pool, and then maximum times is for each episode we need to think of time steps as a kind of it's simply 500 means 500 means we will be looping 500 times, and then 500 times means our loop will run 5. So basically we will take the reward, we will update the Q table 500 times for each episodes. And so we will update the Q value table with 500,000 times in our entire range if the loop doesn't break in the middle of the computation. So to break the loop, we have streaks to end. So if we have 10 episodes for which we have done very nice work, then we will break the entire episodes. And then solve time is if we can at least balance the pool for 195 times, then it is considered as a success. And then discount is gamma factor, like how do we give priority to the reward. The immediate future reward will be much more prioritized, and but the distant future will be much more discounted as defined by this. And if the value is very close to 1, very close to 1, it means that it is a very distant future seeking. So it just tries to seek everything. But if it is 0, then immediate next step will be not considered. So it will be myopic. So it does not explore anything. So if the value is 1, it explores in very depth, in very far future, if the value is 1, so 0, then it does not explore anything. Okay, number of restricts is for that consecutive how many consecutive episodes we have reached the short time. So basically we have successfully balanced the, so basically success history is a kind of queue, we just open it over time. And then select action. So basically select action is a function that based on the state value compute the action. So basically if it is if we randomly, we can take it randomly like this in the if clause, or we can choose the best one, exploration in the first part and the exploration in the second part. So basically exploration is epsilon greedy exploration, and then exploitation is using the previous past knowledge. This indexing will provide array of 2 elements, and then argmax will be written whichever element is higher, so it will be either 0 or 1. And then select explore state. So select explore state means it's kind of it's kind of changing the learning rate and the discount factor over time. So basically what does this mean is that if you can see the exploration rate as defined by the select exploration rate, you can see that the value has been like this, which means that as the logarithmic value, as the number of episodes increases, then the log value will be written the positive value, and as it returns the positive value, the number will be higher, means it will be greater than 1 and greater than 1, and then 1 minus that will be negative. Minimum will be set the negative part, and then but the maximum will set the maximum space. So basically as the iteration increases, we can see that the value is capped at the value of minimum exploration rate, but within that within the range of this 25 over here, then we can see it is I think determining it much more better, right? So where to cut off that value? Yes, so basically also 25. So basically when to cut off the value to the maximum capped value, and then select learning rate is again the same case. So we just sharply decline over here and decrease over here as long as the iteration, and after reaching certain value, we just apply the Elbow method, so we don't decrease much more than that, much below than that, and then bucketized value. So this part is very important. Bucketized. So basically the main it is a repetitive algorithm, and in this algorithm we are given a continuous state of values. Even though it is set continuous, it has a length because computer does not work with the discrete values. So we loop over that, and then we compute the bounded value by computing the bounded values. It is kind of bounding the value, like selecting either minimum or maximum. The values below the minimum will be set to minimum value. Maximum above maximum will be set to maximum value. Value within that range will be value within that range will be left as it is. Similarly, bucket index is done in the same manner. Index below the if we have much more indices below the number of buckets that can handle, we just left it, and then we set to minimum and maximum value. And the bucket index is computed by we compute the bucket width predefined. We know the beforehand because we know the maximum value, the minimum value, maximum value, minimum value, and we compute how many what is the total width, and then and that width is used to compute the indices, like the time steps to compute the values, and then that is computed by the bounded value, and then divided by minimum, and divide by width. So basically if the value is 5, 1, 4, bucket width is 2, 4 divided by 2 will be 2. So we will be using the two different indices. So basically two different indices, and then this is done so that we don't sample any the whole purpose of this the whole purpose is we don't we don't take values outside the range, predefined range, and we don't sample more than that can be handled. So basically we can say that can be handled. So we just take the coordinate at a very in a very precise manner. Now we train the loop over here. Training loop is over there. For the training loop, there is a loop for maximum episodes. Exploration is computed, learning rate is computed. So it is kind of the graph I have shown before. Observation is reset. So if for each episode we start from the beginning of the environment, and then that the current state is assigned as the observation that is bucketized for the so basically for each episode we compute the current state by bucketizing the observation that has been reset just now, and the episode reward is 0, means for that episode the reward is 0, perfect. And for time step in the range of maximum time steps, take some action by using the epsilon greedy policy, then use that action to step into the environment and compute the new observation. What was the reward that was obtained by taking the action, and then what's the whether it was terminated or truncated. If anyone has true, then this is computed in a done is used to mention that episode has been finished, and then let's just ignore for it now. And the next state is actually bucketization of the observation that was just raised by taking the action in the current state of the environment, and then we compute the best Q value, the np.max. So this will the indexing of next state would cause the value to be either 0 if it was not computed before, or some value that was computed before. Then we just index with this index in that array to get the 2 element array, and then we take the numpy max over that array to compute the best Q value. It is either whether the value was best by taking the left action or the right action. So it's just taking the value best of 2, and then the update the Q value is very simple. For the current state is actually the state that we just have to define over here, and that state we are taking the action that we took by using some epsilon greedy policy. We are using the same formula that was defined in our what you say at the Bellman algorithm, Bellman equations, and then episode reward is incremented. For now, for this card poll problem, the reward is always 1, and we are taking some logging information over here, and then after the done is true, we are checking if the success is true. This means that whether the loop run greater than or equal to the some predefined time 195 in our case. So basically this means that we could step into the environment for that many number of times without the dawn being true, without the dawn saying hey it is being truncated, or hey it is being truncated, or let's say as that, and truncated or terminated, and then current state. Actually if we can see the current state, the next state is this bucketized has lots of importance. I will just say or mention in very few times later. History is operated with the value of true boolean, and then if success, total number of string is incremented or it is set to 0, and then current state is actually set the next state, and then this breaks the inner loop if the dawn is being true. and the outer loop is broken after the continuous streak is greater than the that is threshold state we have defined. Now I will explain in depth of the uh, in depth of the bucketization algorithm and how it is important in our case. So basically, in our gymnasium there are environment classic control. There is a card pull environment. Let's just say it is over here. Now uh, I will have to okay, card pull. Okay, basically the card pull has the card pull environment has this observation that has been set to be, you know, threshold. So how this is important is that we are define our state in this variable state bounds. So basically the position should be within minus 4.8 to 4.8. So basically 4.8 to 4.8 and then infinite, so it can be anything and anything, the velocity can be anything, and the pole angle is again 0.400 and this can be infinite. So basically let's say the pole angular velocity, I think let's say it has been infinite, so 22 by 7 3.1 480 degree, that would be very much. So I think the pole does not move too much faster. Let's say it is 0.5 and then 0.5 0.5 and then 0.5. So with this and then after setting this the impact will be in this bucketized state value, because every continuous value that we have obtained in the state value, for each state value length of the state value, we are concerned with bounding that within the range as defined by the state bound. So the value will be within this range for each cases, and then state bounded value, and then the bucket index has also the impact as the bucket width is computed using this range of this value. Now if you can see, this will cause the bucket width to be much more greater, like it will be 100 value, and then divide by the bucket width is then divide the number of buckets. So for this case 50 minus 50 will be 50 minus 50 will be 100, and then 100 divided by number of buckets. So basically our number of buckets is 10. So 10 for that case. So basically 10 for that case. So basically we are dividing 100 divided by 10. This bucket will be 10, and then the value will be subtracted with the original value and then divided by 10 to compute the index for that value, and then this is how it is being done. So the card positions cannot be made more like some arbitrary number. Let's just say it has been in some kind of predefined, pre-computed, let's say some heuristically set value, and then actually we just define it over here like this. And now let's see how the streaks progresses. Like we can close this, and we can see the card being balanced over here. It is saying each iteration, okay, and there are exclusion rates, so we have reached the episode. Let's just wait for 100 episode, and then let's see how the parents are doing. This reward is always 1 for this card pro problem, and then I am not seeing the streak being increased. Let's just see how the pool is being balanced. The pool is being balanced nicely. Execution. just takes much more time, but I think I can change this scenario much more better if I somehow go to the environment, cart pole, and then length variable. Actually have the pole's length. Let's just say the length is too much short, and then run the algorithm one more time to see how does it do. Okay, how is the logs being working? Okay. uh, mm, I think better than unscrollable element, and then I need to see how much step is being taken. Like for episode 36, episode 36 we have 44 steps, so it could not complete within 44 steps. For the episode 37, it took 100, it could balance the pole 18 times, 18 steps, and then for 38 steps, 21, 10, 17, 31, 8, and then 39, 16, 10, 29, 14, 17, 14, 15, 20, 48. So it could not balance in much more steps. So it could only balance for up to 10 times. Okay. 10 steps, 11 steps, 11 steps, 11 steps. I think the solution lies in another mass of the pole. I think mass of the pole is too much light. Mass of the cart, let's say. Okay, now then let's run it. It could solve for episode. We are in a episode. Let's say episode was 0. Episode was 0. Episode for why the scrollable element is not working. Okay. So for the episode 48, it lasted for 36 seconds. 49, 11, 50, 11, 51. It is doing 37 steps, 14 steps. So I think it is balancing well. And now if we had just, let's say, like it's minimum 10 or 11 steps and maximum it is rating 40 or 50 within the episode of 100, right? So after even reaching the 171, it is 9, some 13, 11, 9, 13. So it just takes so much time to converge. Maybe our discount factor is not being changed over time. So basically it is being exploring too much, but the exploration has nothing to do with the Q value problem. Maybe we can do what I thought was maybe okay. I had thought to I just forgot. I had thought to make okay, just now you can see it. So it is okay. So my thought experiment was to not update the Q value at all and see how does it do if it were just being taking the next step randomly, right? So what was the random nature of the problem or the solution? So to see that, I will have to run the loop again, and it is being resetting every second. So basically, if the queue learning was not implemented and the action was taken in a random fashion, where is the school element function not working. Okay, it has to be clicked, right? So 58 episode, it took 18 steps, and then for 59 it took 26 steps. Oh my god, 23. It is doing much more than the, much better than the, if I added nothing. Okay, maybe I can solve it in a manner. There's a discount, right? So select discount. Discount can be discount factor, right? What was the algorithm that I was reading? No, I think I was reading Q learning, and then having discount factor. I want to slide lower than 1, so Q learning is starting with the lower discount factor. You start with lower and then increase over time. Start with lower, increase over time. Start with lower, increase over time means why is it not working? Okay, minus, and then let's just say now we can select discount rate, and then it should have a max value, max of discount rate, that is 0.99, and maximum of discount rate either it should be or max of 0.01, come on. What is okay? Is being decreased, right? So basically I think I just need to it should start from the minimum value, right? So it should have minimum value and then decrease over time, decrease over time, decrease over time, right? Too much sharp, minimum of that, minimum of maximum value, or the here I think getting either it should get 0.01 value or I have kept it just okay. Some value, so 0.5, let's just keep 0.5. So oh shit, max this rate. Oh my god, so it is doing much better. Why am I getting 50 over here? 50, not the 50, it is something like 250. Oh, very nice. 300 maybe. Oh, so sharp curve. Nice, right? So let's just give it 500, and every over thing here will be 250. Let's make it 250, and then run everything from okay. Oh, it's getting your S5. Where is the S5? Okay. Okay, control shape, but update the q value also. Q value table is minus 100 times q value table. What's the thing being done? After how much step? 32 steps, and then 33 steps, and then 34, 14, 32. It's much more balancing with perfect 40, 14. Okay, it is. So basically, it's working much more nice, and I think there have been some kind of improvements, like maybe using the artificial neural network rather than using the table will be much more efficient, because the table has limitation if we increase that. But the neural network will be fixed sized, right? So thank you everyone.